Is this thing on? Ah, here we go. All right. Hey, everybody. Welcome to my podcast or live stream. Nani? Let's go. Do not disturb. 1 hour. Okay. All right. Oh, hello. 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 Hey everybody, welcome to my channel. This is my first time doing a streaming thing by myself, so I feel kind of awkward. What am I doing here? Oh, hello. Happy Friday, everybody. We can do a live, like a real time or a streaming Friday hug. But Happy Friday. I have to do it within the confines of my green screen though. Happy Friday. Oh, thank you. I have a very, very loud keyboard, so we're gonna do a lot of keyboard noise here. All right. I guess let's start, I suppose. So basically, my plans were just to do some hacking on TenderJIT and just look at some stuff while I'm doing it. Yeah, so I guess I'll get started. Yes, keyboard ASMR. Yes. So if you have any questions, just put it in the chat, and I will try to answer the questions. But I'm just gonna hack on this JIT, and I'll say what I'm doing at first, or I'll just describe what I'm thinking or what I'm trying to do and accomplish. So I guess let's get to it. So here's our code. Actually, I want the chat. I can put the chat over here. How do I see that? Okay. All right. What cost? At what cost? Weird. Okay, so this is annoying. When OBS isn't selected, the chat thing goes away. So if I click on my Vim over here, the chat thing goes, which is not awesome. Oh, can I put this here? Okay. I'm an OBS noob. Is that? We can fix this in post, right? Speak my mind. Okay. All right, whatever. I'll just look at the browser thingy. Okay, anyway, so I'm working on this. I'm working on the send instruction in TenderJIT. And basically what this instruction is for sending methods. Oh, and if you can hear my cat snoring, then you can hear my cat snoring. So okay, I'll show you where the send instruction comes from. Let's look at a test program. Actually, I don't want this test program. So if you do foo, and if you do let's say we have take a parameter and we do x dot hello. So we have a method here, and then we have a method call here, and we can print out the instructions for this. And let me make this a little bit wider. I bumped up the font, so it's like, I don't normally program with a font this big. Is it the same as the send method? No, no, no. So this is the YARV instruction, so the low level byte code for sending, like calling a method. So like if you look at this, we have a like, this is the bytecode that represents the foo method. So you can see here it's foo. And if you look at the Ruby code, like, let's pull that over, kind of pull this over a little bit. You can see like right here, we do a get local, which is our X. That's the X get local. So we're calling X right here. That's a local variable. And we'll say like opt send without block. That's like sending a method, or that's saying I want to call this method, and you can see right here it's calling the method hello. Like that's our method. So that means we're doing x dot hello, and then we do a leave. But this isn't like, I've actually implemented this instruction in TenderJIT. Actually, I'm gonna walk back a little bit. I discussed this on the HexDevs live stream, but I want to do, like, I kind of want to cover it a little bit here as we're like working on a JIT. So basically, like, all this JIT is doing is taking a stack machine, which is what YARV is, the virtual machine that Ruby uses. It's a stack-based machine, and it's converting that stack-based machine into a register-based machine, which is what we're doing. So basically, all we're doing is we're taking that stack machine, converting it into a register machine, because our CPU is a register machine. And the idea is that if we emit this machine code, we can speed up our Ruby programs. And I'm going to show, like, I'll show a really basic example of this. Let's see. Let's go to, yeah. Oops. 21. Yeah, there we go. So like, just for people who missed the HexDevs presentation, let's look at translate, this translate thing. Nope. Translate. Thank you. And let's make the font a little bit bigger. So this is like the fundamental of the JIT, or the fundamental idea of this JIT is that we'll take some instruction sequences of a method. So for example, this method add, and here's the method right here, 5 + 3. And essentially all we're doing is walking through each of those instructions and then converting them into machine code and a register machine. So that's all, that's it. That's all we're doing. So today I'm going to be focusing on the send instruction because that one is tripping me up a little bit. And if anybody can help me with it, I'd really appreciate it. I think I'm only going to do this stream until maybe 1, I think, or yeah, probably 1. So hopefully that's plenty of time for people to watch me like fumble. Sorry. Okay. So anyway, back to our original program. Oh God, program. Yes, back to our original program. Let's see. Right. So we have this x.hello, and if we disassemble it, if we run Ruby and disassemble that, we'll see that we have send without block, which is not, let me put that at the top here. Send without block, which is not what we want to do. We want to do the send instruction. TenderJIT already has send without block implemented, so we're not going to look at that. Now the send instruction gets emitted if you do have a block. So let's say we do x.hello, and then we say like boop, boop, like that. So we add a block there. And we look at this, you'll see that now it's like we do get local on X. So you got that X right here. And then we do a send here with the method hello. And you can see it says block in foo. So there's a block there. Oh, thanks, Mark. I appreciate cheers are good too. Like if you cheer me on, I appreciate that. Okay, so we have a block. We have a block here, and then this. You can see this one. Like this thing is new. Oops, this is new from the last time we disassembled this. And this is actually the block, the instruction sequences for the block. So blocks, Ruby blocks get their own instruction sequence objects. And this block has two instructions, and all it does is it puts nil and it leaves. Because the default thing we do is we say like we're gonna put a nil and then we're gonna pop it off. Because you know, like if you have an empty method, like this, it returns nil, right? Question: what shell am I using? I'm using fish shell, the friendly interactive shell. Yes. So right here, like this empty method, if we do this, oh, I guess I gotta save it. Saving the file might help. If we do this, you can see like we got this put nil and then leave. And a funny thing too is like, see these instructions up here? Like the top level program is also a set of instruction sequences. So you can see like we do define method foo. Like this is the instruction for defining a method. It does put object foo and then it does leave. So that's actually the top level script right there. And here's our foo method. Anyway, back to this. So we have a block here, and if we run this, indeed we get our send instruction, and that's the thing that I want to try working on today. Also, I'd like to look at, like, while we're here, I thought it would be fun to look at how method calls work. So like let's do a thing here. We'll do require TenderJIT. So let's do that, and then we're gonna do an example of op send without block, just because like I want to show how the machine code actually works when we're sending a method. So one thing I was kind of confused about when starting to work on JITs is like how does it do this? Question: how do we know that the iseq for the block belongs to that specific hello method? You mean which you mean this block right here? Is that like this block? How does it go to the hello method? I guess I have no idea what the latency is on this thing, so I will just answer. We know that the block in this case goes to the hello method because of the lexically. So as it's parsed, like as the program is compiled, it knows that this block is associated with the hello method. But clearly, like, it may not be. Like, we could do like, if it was a lambda or something, we wouldn't know necessarily. We would have to pass it in a different way. So like, there's different ways of calling a method. So like, we can look at, let's look. So we'll look at the send instruction real quick. So this is. Actually, let's open a new tab. I'm not used to working in a font this big. It's very big. So if we look at the send instruction is like one of the most complicated ones. But what we do is it has to take a look, like it has to figure out what the block argument is. And we can have several different types of block arguments. Like you probably know, like you can do this form, or like, like this form as a block argument, or what else? I don't know, other forms too. So it's pretty complicated to figure out which one it is, but it's all based off of this, like at runtime, the runtime is determined by what is there lexically. Yeah, do end. Do end ends up being the same as the braces. Like the compiler doesn't really care, but yeah. So anyway, back over here, we have to set up the block argument, and you can see like we have to figure out what the block I sequence or the instruction sequence is for that block, and then we'll go ahead and call the method here. That's what this VM sendish thing does. So I wanted to do, let's see, does that answer any questions? Well, I don't know. If you have more questions, just put it in the chat. I will see it and answer it. So I wanted to show like a method call, because I thought this was really interesting, pretty interesting. So if we do like, let's make a new JIT equals TenderJIT.new, and then let's compile this foo method. So we'll do JIT.compile method foo, and then we'll call foo, but it needs a parameter. So let's like give it a parameter. Let's do like class I don't know, hi. We'll have hello return 42, I suppose. Like that's the number, right? So we'll say like foo, and then we'll say let's do hi equals hi.new. We'll do this. Hi. Let's do it like 3 times. See if this works. No. I gotta compile. Or not. I gotta bundle exec compile. This is live coding. All right. So run it, and then yeah, it works. Woo! This JITted. That JIT was so fast. But what I wanted to show, off is not this necessarily, but let's take a look at what the JIT compiler does for a method call, because I think it's pretty interesting, and it's something I didn't know. It's something I didn't know like JITs would do. So let's look at the implementation for it. And in TenderJIT, that is in the IC compiler. Oops, no. We want this thing. So the IC compiler, this compiles one instruction sequence. So for every instruction sequence in Ruby, there is one instruction sequence compiler for it. So when the JIT compiles one ISEQ, it just instantiates one new instruction sequence object. And that instruction sequence object starts compiling, and it can pause and resume, but it's always the same compiler object per instruction sequence. So let's look like, and basically the way this thing works is we have a compile method, and the compile method, this is the very first entry point. Like it compiles, so you do like, actually, let's look at the compile method. Let's walk through this specifically. So TenderJIT, we do a new TenderJIT, and we say .compile, and if we look at this right here, what it does is it casts that method, like it tries to get the underlying instruction sequence. Because if you say like method, if you do like method foo, that returns a method object, and we want to actually get into the data that's underneath that thing. Like we want to unwrap that struct. So that's essentially what this code is doing. It's saying, hey, give me that. And then we're going to figure out what the address of that instruction sequence is, and then we're going to compile that address. And what this thing does is it accesses the underlying data for that struct, and it does this all in pure Ruby. It's all pure Ruby. And anyway, so eventually we may end up allocating a new instruction sequence compiler, a new IC compiler. If it's not there, or if there's one there already, we'll use it. Otherwise, we'll allocate a new one. And that's all it does. And then we say, like right here, I just tried to point at my screen, and then I was like, oh yeah, my my finger is not gonna. Right, right. Ah. Right here, we'll call the compile method on that iSeek compiler. So back over here in the iSeek compiler, we'll run it, and then what it does is it starts like we assemble a prolog which keeps track of any statistics, so we can count like how many JIT methods did we call, how many did we compile versus how many did we call, different things like that, and then it starts doing this resume compiling. So it starts, but it resumes from 0, so we're starting from the very first instruction. Anyway, this resume thing goes through and just like checks each instruction and runs them. Oh, actually, yeah, I should show this. So, I don't know. I put in like a lot of debugging code in here because when you're generating machine code, it's like there's like a lot of you gotta debug it, right? So if we run with -d, we can see it'll show you which instructions it compiled and which ones it ran. So if we run with -d, you can see right here. Oh, that's weird. Okay, so bundler is generating errors. If you run Ruby with -d, it'll tell you like anytime an exception is raised. So this name error was raised and it got swallowed. So like apparently, I guess bundler is raising an exception and swallowing it or something, or I don't know. Anyway, you get some noise here. But so you can see like we instantiated a new iSeek compiler, and then we're compiling this address, and you can see it's compiling this instruction, get local 0, and then it's compiling opt-send without block, it's compiling leave. And then when we run each instruction, you can see like, oh, it's running get local, and then it's running opt-send without block. And then like, I don't know why. Oh yeah. Okay. So the JIT compiler is infectious. I don't know a better way to describe that. What it does is kind of weird to say. What did I change in here? Let's undo any changes. Okay, if we look at this, what it does is it says like, oh, you requested the foo method be JIT compiled, so it does, like it compiles that method, but then any methods we call from that, it also compiles those. So it will JIT compile the hello, this hello method as well. So we'll see right here, like, oh, we're gonna call this, and then, or we compile the foo method, it compiles those 3 instructions, and then it executes the 3 instructions, and you can see here we execute opt-send without block, and then all of a sudden the hello method gets compiled. So it only has 2 instructions, the put object and leave, and then we run those instructions. So it's running put object leave, so that's returning back. So this is the address of the callee, the hello method right here. Okay. Yeah. Let's see. How does it keep track of what has been compiled? So since each instruction sequence has, yes, it is a viral compiler. Does it compile? Okay. Let's start with how does it keep track of what has been compiled? So since each iSeek has its own compiler object, that compiler object keeps track of where it is. So it knows its offset. So we can look at that, like, if we look in here, we essentially just have a while loop that loops over each instruction, and then it may like end. And we keep this ins and index here. This instance variable keeps track of where it is in the instruction sequence. So that's how it remembers. And then a question: does it compile high to? Yeah, recursive. I think recursive is a better. Yes, recursive is a better name. So does it compile high to? It doesn't compile this class, it just compiles this method in here. So like the class definitions do have instructions associated with them, but they only occur like as the class is being evaluated. So like, let's actually look at that because I think it might be interesting. So let's say we just have this particular code. If we disassemble this, you can see like, oh, our top level thing is like put special object, put nil, and then we have a define class. That define class is a result of the instructions down here. So this is like the body. It's like, okay, here's the body of the class. The instructions associated with the body of the class are like define method, put object, leave, right? And then here we have the instructions for that hello method itself. So these methods or these instructions that define the high class, they don't get JIT compiled. So it only compiles things that it's going to execute. Why compile the methods and not the whole class? Yeah, it's an enthusiastic JIT compiler, yes. So why compile just the methods and not the whole class? So the compiler is lazy. We only want to compile stuff that we're actually going to use. So it basically just compiles things, and then like it only compiles what we ask it to compile. In the future, so like mjit will compile stuff when you run a method, n number of times. I think the default is maybe like 25 or something. I'm not sure. TenderJIT, you have to request specifically like compile this method. In the future, I'll make it so it'll compile stuff automatically. I'll probably do that for RubyConf. But for testing now, it's like I just want to do this one, or I want to manually compile stuff. But we only want to compile what we're actually going to use, so we don't want to compile the whole class necessarily. So we don't want to spend time compiling stuff, because the JIT compiler does take time. So that's why we only do a few things at a time. Question: Does the put object represent the hello method or the content 42? It represents the number of, what it's doing is it's pushing an object onto the stack. So it's inside of the hello method. Let's actually take a look. We can print out the instructions for just one method. So if we do ruby vm instruction sequence dot method hi dot dot instance method hello dot disasm. It's kind of long, but that's how we print it out here. So if we print that, just those instructions, jeez, I'm gonna get rid of that minus d. Okay, so if we print just those instructions, you'll see it's just a put object and then a leave, and this is the parameter 42. So we're pushing 42 onto the stack, and then leave pops 42 off of the stack and returns it from the method. So if we had like, we could do other stuff in here too, like true. So if we change this to true, it'll show you like put object and then true. And if we change it to like hello, this is kind of interesting. If you change it to hello, you'll see it's put string. However, put string with hello, so it pushes hello onto the stack. But what's interesting is if we do like, if we do frozen string literals and then run this, you'll see it changed from a put string to a put object. And that's because put string actually dupes the string, so it pushes a copy of hello onto the stack, where put object will push just the string itself onto the stack. Yes, RubyConf is a month away. I know. It's not like getting it to be an automatic compiler is actually fairly simple. I've got that in the test cases. It'll like, I can do it. It's just really like, it's pretty nasty the way that I got it to work. Because this is, so the whole point, or my goal for this JIT compiler is that you could be like just gem install TenderJIT and then use it. So that means like, in order to support that, it means that we have to like it has to hook into Ruby's internals, but it has to do it from the outside. So essentially what I have to do is I have to monkey patch assembly code. So you can monkey patch, you can monkey patch Ruby code, and you can also monkey patch assembly code, apparently, which is a thing that I did, and it's awful. Okay, what is this? Can you show an example of what a temp var would look like in the compiled code? You mean like t equals hello and then return t, or just like something like that? Okay. Yeah, so if we do this, so if we run this, you'll see we do a put object hello, so it pushes hello onto the stack. Then it does a set local for the t, that's the assignment. Set local pops hello off the stack and it assigns hello to t. And then we do a get local here because we're going to return it. So it gets get local, so that gets the value for t, pushes it onto the stack, and then leave pops it off. So the Max asks, is there no function call hook that you can swap in your entry point for? Why do you have to patch assembly? Yeah, there's no hook point for me. No. Interestingly, so my team at work, we're working on TenderJIT, which is a C based. So it's a JIT compiler that's written in C. Though the design is I based the design of TenderJIT off of TenderJIT, but TenderJIT actually we patched Ruby itself, but we're going to be upstreaming those patches. We got approval from Matt's to upstream this, so we're going to upstream TenderJIT, and I think once we get TenderJIT upstreamed, I believe I can use the same hook points that TenderJIT uses for TenderJIT. Let's see. Mark says, so it's all a giant array. Yes. So it's a huge array. That's all it is. One big array. Let's see. Justin says, since the compiler takes time and is in Ruby, are we just compiling subsequent execution? Are we just compiling? I can't see the whole text. Come here. Safari. Are we just compiling so subsequent execution is faster instead of having to interpret each time? Yes, that's correct. And what makes your JIT so tender? It's written in Ruby. It's not written in C. How's that? Okay. So back here. Let's come back to this. This is what I wanted to show. What I wanted to show is how method calls actually work. So let's see. Back here in the IC compiler, so we have for the class or for the function foo. Let's just print out that method foo. So if we print out the ICs for this, it's only a few instructions. So if we print those out, you'll see it's get local WC0, which WC for some reason all I can read that as is water closet. So when I see this name in my head, all I think is get water closet 0. I think I asked other folks on the Ruby core team, what does this stand for? And there's a name, it stands for something, but I totally forgot what it stands for because all I can think is water closet. So anyway, then we call opsend without block. So opsend without block, that's the one that I actually want to look at because I think it's pretty interesting. So if we go look at opsend without block, in here we have the IC compiler has a method for each instruction. So we'll do head def handle opt send without block. So this is the method that handles opsend without block. And this, so I want you to ignore this extremely nasty code right here. I'll tell you what it's for. One of my other goals is to make, so don't ignore it. I'll just tell you what it's for, but it's awful. One of my other goals is to make TenderJIT compile itself. Okay. Yes. Thank you, Matthew. Yeah, it's it's all Ruby. It's pure Ruby. So I want to make TenderJIT compile itself. But the issue is, like, let's say, like, the compiler itself uses method calls, like it calls methods. So if you're doing a method call to compile a method, clearly you have a circular dependency there. Like, how do you break that circular dependency? And essentially what this does is, this is a machine code that patches itself. So it, like, when this thing executes, it says, okay, I'm gonna patch a jump to go to a different location. And that way, when the compiler tries to compile itself, it'll jump back out to the interpreter until it's done compiling, essentially. So anyway, that's not what I wanted to show off, though. What I wanted to show off is how we actually enter this. So, like, if you do this method call here, we compile it. So we say, hey, JIT compiler, please compile method foo, and it'll compile it just fine. But the issue is, like, how does it know the type here? Like, what is X? What is the type of X? How does it know like who to call? Because I mean, we can do hi, and we can do like y. Let's do like another class. We can do like I don't know, omg, and then make this, I don't know, 24 something. Hi to, and this will work, right? So we can do. I will show you. I'll prove that it'll work. I hope it works. I hope it doesn't crash. So if we run it, yeah, it's like it works. And if we do -d, you can see like we compiled, where is it? Right. I should probably print out the class name too, but we compiled one hello here, and then we compile, so it says like compiling put object leave, and then we compiled another one here. So you can see it compiled a second one. But when I asked the JIT compiler to compile this method, it doesn't know what the types are. So like, how do you find it? Oh, Mark is asking, have you interacted with the Ruby Sorbet team at Stripe? Yeah, I mean, we meet with them pretty regularly. I talk to them fairly frequently, yeah. So how does it know the type? And the way that it knows this type is it's lazy. So, like, not ignoring these giant hacks that I have in here, it really boils down, when we compile a send, or when we say, hey, I'm going to do a function call, it really boils down to these instructions. So we have this LEA, and I'm going to explain what each of these are, and we have a jump, because we know when we're going to compile something, or when we're going to call a method, we know that when we're going to call a method, we're going to jump somewhere, okay? So we're going to jump to another method. We're going to jump to another location, but we don't know where yet. So that's the problem. So we want to jump, but we don't know where. And one thing that's kind of odd to think about, or it was odd for me, is that like machine code, you can just like rewrite it. Like, it doesn't have to stay the same. You can just think of it as like a string, and you can mutate strings. So you can mutate machine code too. So essentially what we do is we say like, okay, we're going to put a jump instruction here, but this jump instruction is essentially a placeholder. So once that jump instruction gets hit, then we go and figure out where we need to actually go. So what happens is we say like, okay, we'll jump to this deferred thing, which this is the deferred thing. So TenderJIT actually has two JIT buffers. One is the mainline buffer that runs your code as fast as possible. The other one is for doing deferred compilation. So essentially what we do is we say, okay, as soon as this jump gets hit, we're going to jump into a deferred compiler, and our deferred compiler is right here. And again, ignoring all of these hacks, essentially what happens is it says, okay, I'm going to call compile opt send without block. So it's using this deferred compiler. So this method, compile opt send without block, that's our runtime compiler, I guess, or the deferred compiler. So normally we just use these handle methods. So these handle methods are for when we have zero context. It's like we're just going to compile instructions. And then the compile methods are for like runtime compilation. So we can see like this method gets hit here, and we essentially like, I guess I'm on a branch, but basically on this branch, I was able to reduce op send without block and send to essentially the same compiler. So this thing just goes ahead and calls compile send, but we can see like, let's do like puts, hi. So what we'll see here, we're not going to print these. I'm going to get rid of these prints. What we'll see is that when the lazy compiler is hit, it'll print out hi. So we do that. If we run this, let's get rid of the dash. Well, I guess let's do this. So you can see hi that hi is run. And if we run with -d, you can see the order in which instructions are executed. So you can see like, okay, we compiled get local, we compiled op send without block, we compiled leave. Now we're running get local. Now we're running op send without block, and this one is going to hit the lazy compiler. So we see hi printed out here because the lazy compiler got hit. Lazy compiler goes ahead and figures out what the receiver type is, and then it compiles the target method. So if we go back over here to the lazy compiler, we can see like essentially def compile send. We can see like right here we figure out what the class type is, and we can do like p. Let's do p. This class is actually a pointer. It's just going to be a number. So if we do like puts class, this will be a number. But we can do like p fiddle.dl unwrap class, and that'll print out the class type. So we can do this. So if we get rid of the -d, we'll see right here we have that hi class. So this is the address of the hi class. So there's hi, and then here's the OMG class. So we're able to determine what the class type is at runtime inside of the lazy compiler. MaxP, is this a template compiler or do you have an intermediate CFG? This is a template compiler, but it uses a technique that one of my colleagues developed. Maxime developed. It's called lazy basic block versioning, or LBBV. And basically what it does is, so this is actually a really cool trick. Like if you have a method, so let's say you have a method here that has an if statement in it, like if omg, or if like x dot hello. So what'll happen is the compiler will come in here and it'll actually pause at this branch. So it'll say I'm gonna pause. And it'll resume later. So actually let's check it out. We should be able to see it in the debug output. So if we do like puts hello, not hello, I don't know. So we'll do like true, and down here we'll do false. Let's just compile it and check what the output is. So if we just compile it, man, I wish it did not have all these like things. Anyway, did it compile the whole thing? I think it might have. Because the branch and less is a little bit smarter. Compiling put string. Oh, looks like this one's being very eager. I'm not sure why it didn't pause. How can we get it to pause? I can't remember. Anyway, it will pause sometimes, which I can't remember when. And then it'll lazily evaluate each side of the branch. I'm not sure why this one isn't compiling or isn't pausing. I guess it figured it didn't need to. Well, let's try running it and see what happens. We'll do puts foo hi. So this should hit one side of it. If we run that, did it resume compiling? Let's check. Let's do this. Def resume compiling. Run this. So that's resuming at 0. We don't care about that. These are both resuming at 0. Yeah, I don't know. I don't know why it's not pausing, but it will pause sometimes on branches and then keep going later. Okay. What were we looking at? Methods. Handle opt or no, def compile opt send without block. Here we go. So in compile send, we go look up the type. Which, did I delete it? Yes, I did. Good for me. All right. So anyway, this is how it'll find the instruction sequence and go off and compile that method. For the error at the top of the output, do you need Wharf installed? It is installed. It's just like Wharf is installed. It just, I don't know, man. It's just errors. Anyway, all right. So let's work on send. I only have like 15 minutes left, but let's do it. I have some stuff stashed here. So I started implementing send with blocks. Because the reason I'm doing this is because I'd also really like to get opt-caret benchmarks working for RubyConf. So we can run I'll show you opt-caret. Actually, I had to modify opt-caret a little bit, but I'll show you all what the modifications are, so you know I'm not not trying to cheat. So we can run maybe it can't run opt-caret. Did I fix that? No. What did we do? Oh my gosh. Let's stash this. Git stash. Okay, yes. So I clearly messed something up. So we can run opt-caret, but let's look at the file itself. So right here we say I had to tell it, hey, I want you to compile the run method, because like I said, it's not it won't automatically compile it. Question is, so you're working on YJIT for work and TenderJIT in your spare time? Yes, that is true. Yes. So I asked this, hey, run the run method or compile the run method, then enable the JIT, and then this is the normal code, right? And then down here I wanted to see why is it quitting? Why is it quitting the JIT? And we can see down here the reason is we're hitting complex methods, basically method calls I don't know how to handle yet, and that's specifically these blocks, or methods with blocks. Okay, so let's do test.rb. So this is kind of one of them. I got some of the send methods working. So if we do test instructions send test. So this is I got some of them working. Actually, we can delete that, which I'm not going to do because I don't want to mess up my stash. So this'll work, and then we can yield, and it'll return the right value. So these cases work, but the one that really doesn't work is when you do well, let's just. If you do, did I have a test in here? No, I was trying to figure out what exactly was broken. Here it is. So blocks that take a parameter do not work at all. If we look at this, it's really funny. So working on this is really funny. You get some really odd errors. So we'll do this, compile each. We're just passing in an array and then summing the numbers, the elements in the array. And if we run this, let's just run it here. If we run this, it's it's not going to work because the method doesn't exist. Good job, Aaron. Happy Friday, right? Woo, Friday. So if we run this, it's like, we can see from the debug output here, like it compiled a bunch of stuff. That's great. Like, really compiled it. That's cool. And then it runs some stuff. It's running send. But you can see like plus, this is plus, no implicit conversion of integer to array. And you're like, what? Why? Integer? Like, what? And then if we do like, oh, it's not even summing them. I'm just doing +1. Let's do like m. Okay, still, I mean, still, it's mad about this, mad about integer to an array. And if we do like, let's do p omg m, or no, I is our problem. If we do that and run this, it says I is the array 1, 2, 3. So you can see like, we got some problems. And I did like very cursory research before doing this live stream. I have no idea if we're gonna fix it in the next 10 minutes because I do have to go. But the problem is, the issue is that we've messed up the stack, so it doesn't know, like, it's trying to find this I thing, but instead of finding I, it's finding X. So we're looking this up incorrectly. And what's happening is, like, when we compile this block, when we call into the block, we need to set the stack at a certain location so that it knows, like, when it does an offset into the stack to find the local variables, it finds the right thing. So what I was looking through is, let's see, let's do Oh, wait. No, there's one more thing. You know what? We're not going to fix this today because I want to show off another cool thing. Or the other cool thing from calling methods that I really liked. So back here, this is my favorite. So far, this is like, I really like this. I really like this hack, but it's probably not that great. Like, so this compile send, when we call compile send, it has to go back and patch that original jump. Like, I missed discussing this. So it comes back and it rewrites this location right here. Right here. And we'll do like, but it's like, how does the deferred compiler know what to patch? Like, how does it know where to patch something? We have to tell it the address to patch something. And that's what I'm doing right here. It's using this LEA to determine the location of this jump. And I'm going to put a breakpoint here, int lit3. And there's a special, like, there's a special machine code, like special CPU instruction that will break inside of debuggers. So that's this int3. There's an int3 instruction. If we do this, like, we can do, and yeah, of course I got this giant like thing here. If we do this, oh, not test. Well, yeah, test is probably fine. Let's do this. If we do run in LLDB, it stops right here. So you can see this LEA instruction. That's right here, this instruction. And what it's doing is it's reading the instruction pointer, RIP, and loading that value into the RAX register. So this number right here is where we are in the machine code. Like, that's the buffer that we allocated. That's the address of the buffer we allocated. And what we want to know is, we want to know this location here. This is 0090 because that's where the jump is. And you can see the jump is going off to some address here. So if we step 1 instruction, you do SI, and then we print the value of racks. You can see that it's 129FP0090. So it's this thing here, right? And then when we call into the compiler, essentially we just pass the value of racks into the compiler. Now let's do it right here. Like, what do I want to do? There is a way. Oh, Does this mean metaprogramming Ruby is an optimization challenge for the JIT? I mean, mate, kind of. I mean, it's just like checking stuff at runtime. Like if you're to do a like metaprogram like a ton of methods, like maybe you could blow out your memory or whatever, but it doesn't, like the JIT doesn't care. You can metaprogram to your heart's content. Like go for it. Something I did with send versus send without block. No, it's like I'm setting up the stack frame incorrectly. So like when you call into a block, you know when you're in a block and you do like puts caller, you can see that the block is part of that stack frame or part of the caller. I'm basically setting up the stack frame incorrectly. So the stack frame contains the or the frame contains a pointer to the stack itself, and that or to the Ruby stack where we push and pop things. That pointer is wrong, basically. So, all right, so back to this thing. Like when we go back into compile send, we pass the value of racks in, and there's a way to disassemble. Let's look. Yeah, nice. So in LLDB, you can say like disassemble, and then you can give it a start address, and you can say how many instructions you want to disassemble. So I'm going to start here at this 0089 instruction. We'll do disassemble. Actually, no. Let's put another breakpoint here. So the deferred compiler is going to compile the method, jump back, and then like patch the original jump, and then jump back into the mainline JIT. So the first time the method gets called, this deferred compiler gets called. The second time, it's not there anymore. So let's do we'll do an rt.break. So this makes a second breakpoint. So we got a breakpoint here before we jump into the deferred compiler. We got a breakpoint here after the deferred compiler returns. So let's run this. So this is before it runs. Like this is before. And if we do disassemble start address, this address, and then we say how many instructions? Let's do count 4. So we'll do that. And you can see here, here's the LEA, here's our jump, our pop, whatever, right? So I'm going to do continue in LLDB, and that'll just continue until we hit the next breakpoint. So we'll do, oh, and take note, like I want you to note this address right here, this jump. So it's jumping to this address. Boop. All right, so if we do continue, so we're outside of the deferred compiler now. If we run this, if we disassemble again, you can see like at 0090, we had a jump to B4000. And now at 0090, we have a jump to 00C0. So the deferred compiler was able to say like, hey, all right, now I know where the method is. I'm going to go compile all that stuff, and then I'm going to patch the original jump location. And now next time this machine code executes, we're just going to jump straight to the method implementation. And I thought that is very neat. Okay, I guess we're almost out of time here. So what I'm going to do is we're going to look at the send instruction just a little bit. And I'm going to show you exactly what's missing from the send instruction, like where the stack frame is getting messed up, and then end the stream because I got stuff to do today. Let's see. So what I want to look at is, let's go to Ruby insns.def. So I know that setting up the block is okay. Like we can set up the block. And if we go jump to VM sendish, VM sendish was getting this value MEXP search method. So that's important because we have this like weird switch statement. So it's like this. No, I care about this one. VM invoke block. That's what we want. If we go look at VM invoke block, The block handler that we're using is an iSeek block. These are the different types of blocks that you can have. One is an iSeek, one is an iFunc, which I'm not sure what that one is. Like, I gotta figure that one out. Proc, you can have a proc and a symbol. If we go look at the iSeek block, because we just wrote straight in Ruby. If it's pure Ruby, it's an iSeek block. We have this here when we're invoking a block. This code here is setting up the frame to call into a block. What it's doing is it's saying like, okay, we're gonna get the current stack pointer for the current frame, so that's the caller's frame, and then we're gonna subtract off the argc for it, and then where we're getting messed up, or where I'm getting messed up, is when we push a frame, we have to add on the arg size for that. So this RSP adjustment, like I have no code for that, and it's just because I didn't write a test for it, so I got a test now, and I got to fix that, but it's this adjustment here that's broken. Okay. Oh, thank you, Monique. I have never done streaming, but, well, by myself. I've done streaming with other people. All right, I am going to stop now. Oh, thank you. Next stream, I'm not sure. I mean, if people are happy about this, I might do it again. Oh, stop it. No, do not disturb. I don't know. Maybe in a week or two. We'll see. We'll see. I haven't decided yet, but I'll tweet about it. Anyway, thank you all. I really appreciate everyone for coming and saying hi and stuff. Happy Friday, everybody. All right. I'm going to end the stream now. Bye.